We okay? And the base provides that electron pair. It's the Lewis acids that are different, right? And I made this solution with HCl, and it became acidic. Did I add a Lewis acid? What was the Lewis acid that I added? Hydrogen ion, right? The HCl provided hydrogen ion, but it wasn't the HCl that was the Lewis acid. It was the hydrogen ion that was the Lewis acid, because it's the electron pair acceptor. Are you getting it? It's confusing. 3 different theories. You have to think about it. The hydrogen ion is an electron pair acceptor. It's just not the only one, is it? We have lots of things that can accept electron pairs, like positive ions, and other things as well. Okay? And how could a positive ion affect the pH of a solution?
Make it go down.
How could it affect this balance between hydronium and hydroxide that exists in water? Before we ever added anything to it, it exists in water. The positive ions can do what? Attach themselves to hydroxide ions. And when they attach themselves to hydroxide ions, they remove the hydroxide ions from the solution as hydroxide ions. So the hydroxide concentration goes down, and hydronium goes up, and pH goes down. Right? So positive ions added to water can change the pH. And what is our guide as far as whether or not they're going to change the pH? Solubility rules. Because the same thing that causes iron ions to attract themselves to hydroxide ions and lower the pH is also what makes iron ions attract hydrogen ions to form hydroxide ions to form a precipitate. I'm not helping when I make mistakes like that, am I? Let me say it again. The same thing that allows iron ions to attract hydroxide ions and lower the pH is the same thing that causes iron ions to attract hydroxide ions and form a precipitate. Right? So for instance, iron ions together with hydroxides, not very soluble, because iron ions are a strong Lewis acid and have strong attractions for hydroxides. And that's what makes it precipitate with hydroxide ion solutions. On the other hand, sodium ions don't have a very strong attraction to hydroxides. How do we know that? Because they're weak Lewis acids. How do we know that? Because sodium ions and hydroxide ions are very soluble together, aren't they? So sodium ions must not have much of an attraction for hydroxide ions. We okay? How can a negative ion affect the pH?
It can raise it. Attach to that hydronium.
Can do what? Take a hydrogen ion away from water and make more hydroxides, or take a hydrogen ion away from hydronium and make less hydroniums. Either way you think about it, it works out, huh? If I take water and add negative ions to it, it can take hydrogen ions away from hydroxides, turn them into water. That lowers hydroniums. Excuse me. Do it again. If I put a negative ion in water, it can take hydrogen ions away from hydronium ions, turn them into water molecules, and lower the concentration of hydronium and raise the concentration of hydroxides. Or the negative ion could take hydrogen ions away from water and turn them into hydroxide ions, which would raise hydroxides and lower hydroniums. It's the same thing, isn't it? Okay? And what is our way of determining how good a negative ion is going to be at doing that?
Solubility.
Our acid-base chart. We can get a better measure. Solubility tables just say yes or no, right? Soluble, not soluble. So we don't get as much from that as we do from our acid-base chart that lists the bases in order of strength, huh? Right? How we doing? Okay, good. Acid-base indicators, new topic. Acid-base indicators are chemical compounds that change color depending on the pH. Acid-base indicators change color depending on the pH. Excuse me, they're chemical compounds that change color.
Do you want to give me that? Just keep it first. Okay. Thank you.
For instance, phenolphthalein is one that you've seen me use before. I used phenolphthalein when we dropped sodium, lithium, potassium into water, remember? Okay. Phenolphthalein is unusual as an acid-base indicator. Most acid-base indicators have two colors. One in acidic solutions, one in basic solutions. They may appear a different color as we lose one color and gain another, right? For instance, if one is yellow and the other is blue, as they become equal, those two colors, it looks sort of a green color, for instance. But there's really just typically two states for the acid-base indicator. We'll go into this in more detail when we talk more about equilibrium. But for instance, this is what's called bromethymol blue. Yeah, I know. It's not blue.
Yeah.
I'm going to add a little hydrochloric acid. This should be lowering the pH. No change. That's because the yellow form of this acid-base indicator is the acidic form. If I add some sodium hydroxide, on the other hand, and make the solution more basic, it changes to blue. Now we're looking at the blue form of the acid-base indicator. If I add hydrochloric acid again to lower the pH, it changes it back to yellow. If I'm careful about adding it, we might be able to get it to be sort of equal amounts of the acid and the base form.
No.
I added too much.
It's getting all stuck in that little...
That's going to be too much. This has smaller drops, so let's see if we can. These solutions are both 1 molar solutions, so they're pretty concentrated. That's green. That's green. That's green. Now what we have at this point is equal amounts of the yellow form and the green of the blue form together, and that's why it looks green. Okay, bromethymol blue, an example of an acid-base indicator. Phenolphthalein is fairly unique among acid-base indicators in that the acid form is colorless.
Seems dangerous. Feel like it's colorless, so you don't know if it's neutral or if it's an acid or how acidic it is.
Well, we'll find it's very handy at doing what we need it to do. Acid form, this is hydrochloric acid. The acid form is colorless. Do you remember what the base form looks like? Pink? Uh-huh.
Yes.
That's the base form. Now we'll find out a little later in the period why phenolphthalein is a handy one for us to use. You have other acid-base indicators. How many of you used a kit like this to measure the pH of your swimming pool or hot tub? Okay. It uses an acid-base indicator called phenol red. Phenol red changes from a pinkish purple color to a yellow color between a pH of 6.8 and 8.2. And in between, it's sort of an orange color when you're a mixture of those two. And because we need to adjust the pH of swimming pool water to about 7.6, it's an ideal indicator to help us with that. Now, why am I saying that? For instance, I'll estimate that the pH right now in this solution is about 10. Oops. 12. On its way to 13. What color change have you seen? It might get a little darker, but not really very much. An acid-base indicator is really useless outside of the range in which it changes from one to the other. Phenol red, for instance, changes between a pH of 6.8 and 8.2 from a yellow color to a pink color. And according to the color scale, which is right here, the pH is, well, between 7.2 and 7.6, which is a good swimming pool and hot tub pH. Any idea why we care about pH in a swimming pool or hot tub?
Just don't burn yourself when you swim.
No.
Dive into a pool.
Because you're not going to burn yourself in a pH of 8 or a pH of 6. Rainwater, for instance, has a pH of about 5.5. So why do we want to be so careful about adjusting the pH of our swimming pool? What is it on your body that is so sensitive to pH? Any idea? Made of? Protein? You, of course, know that proteins are chains of amino acids, yes? Amino acids are an acid at one end and a base at the other. And because they are both acids and bases, proteins will dissolve in both acidic and basic solutions. And the ideal pH for proteins staying in one piece is right around 7.6. If you get more acidic than that, the proteins tend to fall apart. You ever made the mistake of washing your hair with hand soap? You know, you're out camping someplace and there's no shampoo and you go, well, I've got some hand soap here, some ivory. What's the worst that could happen? Ooh, your hair ends up just feeling terrible. That's because hand soap is fairly basic. And the protein in your hair starts to degrade.